Hello everyone and welcome to this video. This video is about materials modeling using ABAQUS CAE. In this video I will show you three different ways you can use to identify material parameters or define material behavior in ABAQUS CAE. The first one is for hyperelastic and viscoelastic material. ABAQUS CAE has a capability to identify material parameters and also check for the stability of the material model. So I will show you one of those examples. In the second case, if you have a metallic material which shows a elastic plastic behavior, then how you can really directly import that data into ABAQUS CAE coming from experiments, and how you can really then use ABAQUS CAE to identify different parameters required for an elastic plastic material model. Lastly, if you can't use any of the above two for different types of model, because not all the models can be used for the first two bullet points, so in that case you can manually identify material parameters, and I will give you one example on that. And finally, if you are working with UMATs, if you are an advanced user and you want to use a UMAT or VUMAT and you have a large set of parameters, then sometimes it's useful to use or interface different optimization tools with ABAQUS to identify those parameters. So I'm not going to show you how you can do it in this short video, but I will show you what are the different options, and maybe you can try on your own, or if you have any questions then you can get back to me. So let's jump into the real case, and now I will show you in ABAQUS how you can do all these three different things. Okay, let's start with the first case where we have, let's say, a hyperelastic material data. Again, this is a fictitious data. I'm just assuming things. There is no discussion on the correctness of this data. So I'm going to use this data which I have created for a artificial hyperelastic material, which could be a polymer or a biological material or whatever. So what you can do is you can go and create a material. You can select a hyperelastic material here. As you can see, you have different options, and not all the options can be used to identify material parameters, but I'm going to use hyperelastic material. And this is hyperelastic, so you go to the mechanical, elastic, and then you select hyperelastic material, and here you can just say test data. So I will say that I have a uniaxial test data, and it's a nominal stress strain. So if it's not nominal stress strain, you can convert it to true stress strain. Again, you can use the relationships there, or you can use ABAQUS as well, which I will show you later on how you can do it. So I'm just assuming it's nominal for the time being. Okay, so I just copy paste the data here, and that's there. So, and I will say that okay, it requires it's an unknown test data or something like that. Okay, and now I go and select OK. So now my material definition is here, as you see, which is a hyperelastic material, and I can press evaluate. So if it's not, it cannot evaluate, it will give you an error at this point. Since I have only a uniaxial data, so maybe I can remove this, or I can keep it, whatever, it doesn't make any difference most probably. And I need to identify, I have given the source input as this, and I want to identify, let's say, parameters. Let's say if I'm going to use a polynomial of second order based on Mooney and Rivlin, or I'm going to use Ogden type model and I'm going to use 3 terms or 6 terms, then how it looks like. So let's try these 3 models, right? And I want to identify the parameters for those. So when I press OK, it will start evaluating and identifying the parameters for these 3 models, and it says evaluation failed. So see the data file, right? So there was some issue with that, so I can go back and see what is the issue with the data file. So again, I can go here and I can find out where is my data file, and it's here. So I'm going to open it and I will see what's written there. Ogden test data input did not converge for N6. So you see the error is for the N6th order thing, it didn't converge. So let me go back and change the value. So if I go back here and I just say evaluate, and instead of using it for 6th order, maybe we can use it for 1st order and 3rd order, and see how it looks now. So if I use these three orders, so it seems to be working. You see it's trying to converge. So if I now, this is the output window now, and you see all the graphs with comparisons behind. So this is for the polynomial order 2, and it has given you the coefficients which are identified for this case. However, it gives you an error that it's not stable for uniaxial tension case or compression case as well. So this is not stable, so it's not good to use this model. So let's go for the Ogden type 1. So you can see it's pretty stable, and these are the parameters it has identified for that. If I use third order terms, then again this is stable, and I can use these parameters. So once I have these parameters, I don't have to worry about the stress strain curves or something. I can just go and use these parameters directly, which is mu1, mu alpha, and d for different orders. So since this was third order, I can remove the output curves. You can again see what are the comparisons really mean and how they look like. So I can go, and now I can basically define my own material, which is hyperelastic, and I can say that okay, I'm going to use Ogden model of order 3, right? So coefficients, and I can say it's order 3, and I need to find mu1 alpha 1, mu2 alpha 2, mu3 alpha 3, d1, d2, and d3. So I need these parameters for this model now, which I already have identified directly from this evaluation from ABAQUS, and this I can again access through visualization, right? So this is how you do it, and I hope it was clear. If it's not clear, then you can always get back to me and we can discuss it further. All right, so this was more about that. If you want to further play around with it, then you can do that. So now let's move to the next case where we have an elastic plastic material and we want to really take it to ABAQUS. So let's say this is elastic plastic material. I am using this data here as an elastic plastic material data here, and this is plotted here as you see this blue line. Okay, so I've just copy pasted this data into my ABAQUS thing. So you have to go to calibration, create, and then you name it, and then it will create a calibration section here. So I have created an elastic plastic section here, and if you look at the data here, so you will find out you can just say that data and create, and then it will give you this table, and you copy paste it here. So you see I have copy pasted the data already. It looks something like this, as you see, as I showed you here, and elastic part is a linear, so I just use 2 or 3 points there. So this is my data, and I can basically, again, if I'm not sure, I can plot it. I can also process it, as I told you before, if it's a nominal data, and if I need, for example, ABAQUS requires true stress strain data in many cases, or for plastic part it requires true stress and logarithmic plastic strain. So you can convert those using these options. So if you press convert here, and you can convert it to nominal, or you can convert it to a true form, and then it can save it for you. So that's what I have done here. In this case, I'm assuming whatever I require is already there. So now what I do, I just say, okay, I want to create a behavior based on this experimental data which can be used by ABAQUS directly. So I just create behavior. So when I create this behavior, it will ask me for the name, and it will open this window here, right? And now you see there are different things here which needs to be defined. The first thing is the ultimate point. So you can define that point here directly. So it's using, first thing is you need to give the data set, and I already have a data set 1 which I have inputted in ABAQUS right now. Ultimate point, you can ask it to compute itself. So sometimes it will not be able to read the values. Here in this case, it's not giving you the right value. So what I will do, I will just identify myself. Then normally it works, but in this case it's giving me a hard time. So it depends on the data. You see it's a fluctuating data, so it's giving me a hard time on that. So if I say this, okay, so let's click on this. So now my data is somewhere here, so I have defined the ultimate strength. Now the next thing is the yield point. So again, yield point should be picked up by this thing, but since you see it's a fluctuating data for a complicated alloy, it's struggling. So I'm going to use this point here. So that's what I'm going to do now. I'm going to select this point here, and now I have ultimate yield strength value as well. For the number of points for the plastic part, because you need to define the yield strength at 0 plastic strain and then the plastic part of the curve. So you basically can, so it's basically selecting those points in this case. So you can increase the number of points, and you can see it's trying to pick up those points from here, and these are very much what you require in this case. So it goes up to 0.05. Once you have done that, you can also define the Poisson ratio, but since it's a metal, so I can define it personally. But for Poisson ratio, you need the lateral test results as well, so you need to measure the contraction in the lateral direction. In this case it's a metal, so I'm just assuming it to be 1. And then I say that create a material model 1 using these properties, right? So directly using these properties. So I have done that now, and now they have created or mapped all these parameters which I have identified from my experimental data are mapped in material properties 1. So now if I go to material 1 here, I should be able to see what are the elastic properties which were given, which identified, and you can see all the plastic part of the curve is already there as well. So ABAQUS can do it directly as well. I have been not using CAE for a long time, so what I used to do was, you know, there are many different rules to identify the yield point. R 0.2, so you basically measure 0.2% and then you go parallel to the elastic line and you identify the yield point. So you can use that thing as well, and then from that point onwards is your plastic part. So your first yield point is that point at a line which is parallel to the elastic line and at a distance of 0.2 times of the strain, and then you read all the other values, and that gives you the same table as you have defined here in ABAQUS. So you see at the first yield point your plastic strain is 0, which is that R 0.2 thing. Some people work with RT 0.2 some standards, so again in that case you don't go with the parallel line, but you basically go with the 0.2 distance and then you go vertically up. So again you can look at the standards and you can find out how you do it, but in this case you can see ABAQUS can identify this. If your data is giving you a hard time, you can basically do it manually as well, as I showed you here. For automation, again your data should be as smooth as possible, so you can make your data smooth by using process, and you can try to smooth it down, you can scale it, you can truncate some problem areas which I haven't shown you here, so you can play around with your data. In this case you can see it's a fluctuating data, so it was kind of struggling. Alright, so I hope it makes sense to how to identify or define or create a material model directly from ABAQUS using experimental data, and this is how it looks like. If you have any questions, again, get back to me. I might be very fast, but this was just due to the duration of the whole thing. So now we have discussed two things. We have identified that, okay, if we have a kind of a hyperelastic or viscoelastic model, how I can use ABAQUS to identify the parameters if I know the experimental data or test data for uniaxial, biaxial and triaxial cases. For the second case, if you have an elastic plastic material, you can directly import this curve, whichever you got from the experiments, and identify manually, or sometimes ABAQUS can automatically identify it for you. What are the yield points, plastic part of the curves, where is the ultimate strength, etc. So I hope this is helpful and you are able to define your material parameters using that. If something is not clear, again you can comment below and I will try to explain it to you. Now the third case is if you have a model which cannot be evaluated or cannot be transferred directly from experiments into your model. And one of the cases, as I explained, one of the model is Johnson and Cook model. As you remember, that your yield function is defined as this kind of relationship where A and B and N are material parameters which have to be identified from experiments, and epsilon plastic bar is basically the equivalent plastic strain. This is the temperature or thermal softening term. In this case we will be working with isothermal case, or no heat will be transferred. So I'm going to use the same values for these two temperatures so that I don't have any effect because of this theta hat term or temperature effects or temperature softening. Okay, so we need to identify these three parameters. So old-fashioned way, because it's an easy model, what you can do, and it's a one-dimensional model, so I can just play around with I can create a function based on that relationship before, and I can identify those parameters here, right? Easy peasy in Excel. But imagine if you have a complicated model, you have multiple data cases, let's say you have a strain rate dependency as well, then it might not be that easy, or if you are dealing with stress tensor. So in that case, what you can do is you can, let's say if I have the same uniaxial data which I showed you before, this part, right? So I will go, so now I will move to that model where I have to use non-default material model. I have to create a representative model for the uniaxial test. So this is a uniaxial tension test curve which I just showed you before. So I created a part as I do it before for any model which is a cube. So it was just like create a part, 3D deformable solid extrusion, and this part is 1 by 1 by 1 millimeters right now. So everything is in millimeters. Then I go to the properties and I define the elastic and plastic part as I normally do for any other material model. So elastic part, again, I can identify from experiments, or if I know the material, generally elastic constants are known, so you can use those values here. Plastic part is the more tricky part. So you have different options. If you remember, you can directly define plasticity using yield strength and the plastic strain at that yield strength value. But in this case, we have opted for that because this can be used for dynamic behavior of the material as well. So that's what I'm doing here. I can start with, let's say I don't know the values. Right now I'm using the accurate values, so it might give you very close results. But let's say I didn't know any values. So I start with, let's say 500 and 600 something, and let's say 0.9, and I use M, and then for transition temperature and melting temperatures I'm using these kind of things. So everything is so that this has no effect on your softening part, on your stress behavior. Okay, so this is material I have defined. In this case I have no idea what properties are. I go to assembly, I bring the part here which is just one element, one cube. I created a step and I'm using a general step in this case, and you can see everything is default. Only I'm using time increment minimum and maximum to be 0.1. Other than that, everything is default. For there is no interaction since there is only one object. For the loading boundary condition, I have defined the boundary conditions as a uniaxial case because this is the test data I have is for a uniaxial tension test, right? So what I do is I will fix this surface. I can fix this surface, and maybe I can fix one of the two surfaces from the top or from the bottom, and then I will pull from one direction. So I have to keep two of the flat surfaces free because it's a uniaxial tension case. The same can be applied for compression. The displacement boundary condition will be opposite. So I show you what I have done for the first boundary condition. As you can see, it's a U1 direction, and I have fixed this thing because this is normal to the U1, so I have fixed it in U1 direction and it remains flat. For the second case, it's a U3 direction since I have fixed this surface in the U3 direction, so it will be fixed in that direction so it doesn't move. And the third one is the bottom surface, as you see, and it is fixed in the Y direction only. So by fixing these three surfaces, what I have done is it can expand in this direction or contract in this direction. So if I expand it or pull it in this direction, then it can also contract literally. So it's more like a realistic uniaxial test. And finally, I apply displacement boundary condition based on the test data. I have one total dimension is 1, and I need to apply total strain of 0.05 or 0.056. So I have used 0.06 based on that, and it's a ramp analysis, so it increases linearly with time. So my uniaxial test representative simulation or model for my uniaxial test is ready to go. I go and mesh it, and again I use a mesh with, I define the part seeds, and in this case I'm using a global seed of 1 because I want only one element in my simulation. All right, and then I mesh it. So this is the mesh for me, and then I run it. All right, so if I run it now, so this is the model with no default because I'm using this one. So if I run this thing here, so it's submitted, it's running. I can monitor it as well if I want to, but I think it's a very simple test, so it will finish soon. It's just a one element test. Okay, so it's completed. I go and I see if my model is behaving. So it should expand in this direction because I'm pulling in this direction, and it should contract in the lateral direction. And that's what you see here. So it is doing this thing. So when I pull in this direction, it starts to contract. in this and this direction. So that's what you see. So all my boundary conditions are okay. This is too small, so maybe I will make it bigger. You go to the viewport annotate manager and then set font. To save time, I'm just going to select all of them and I will increase their font to 36 to be more visible. Okay, so this is how it looks like. Now I need to plot the stress strain curve of this element to see how different it is from the experiment. So if I go to the manager, all right, so what I have to do is now I have to go to the ODB database. I will select LE33 because it's the 3 direction where I have applied the loading, and also I will select S33, right? So S33, then I will save the data for this one element. I have to select an entity, so I go here and I say okay, there is only one element, so I just select element number 1 and I press save. Now I have stresses and strains as a function of time, so I need to combine them. So I go to operate on XY data and combine, and I think it's better to make an absolute value. So I will start combine absolute this, and then I can use another absolute value, then I save it. And now if I plot, I should get a stress strain curve which is elastic plastic, and you can see how it looks like. The font is too small, so again you can double click axis title maybe, and then you can increase the font, and you can do the same for the axis as well. I think it's too small, maybe I will just create it 48 or something, and I do the same for the horizontal axis. Now axis is more important for us because we know it's stress and strain all the time, so again I do it this way, and that's pretty much it. So you see my stresses are 500 and it goes up to 0.505 or something. So now let's bring the experimental data, right? So okay, so what I do now is I can say that I wanted to get it from, let's say, keyboard, and I go to my Excel thing and I can copy paste my stress strain data. Okay, so that's what I do here, and copy and then paste here. So once I have copy pasted, I have to tell what is what. So first column is strain, as you remember, so I will select the strain here. The second column is stress, so I go with the stresses here, and then I say plot, and I will also say save, and I call it experimental. All right, so experimental data is there and it's there. So now I can compare with experimental data and my XY data. You can select multiple things by keeping the control button pressed and then click with your mouse onto a specific thing, specific data, and you can see now it is much lower than what we were expecting from the experiment. So this is my experimental part. Maybe if it's not really visible, you can go, and if you go to XY option, curve options here, you can have some kind of markers which can help you more to identify what's happening, and also maybe you can change the style of the line. So this is your experimental curve, as you see, while this is the simulated results. So now what you will do, you have to now go back, change the parameters, rerun the simulation, come back again and plot the results and see how far you are, and then you keep on playing around with the parameters to find the material parameters. You can do it this way. Some parameters you can directly read from the paper, for example curves, for example the initial yield strength or hardening or ultimate strength, as we did before, but again sometimes you have many number of parameters and you have to do it manually and it takes a lot of time. Okay, so it's a tedious process, but you have to do it. So now what I will do, I will go back again, let's say, and I'm going to redefine the material parameter. You can make all the process automated if you know Python, and there are many videos on that in YouTube, so again you can have a look. I don't want to spend time on that. So let's say I use something close to what I see in the curve, and maybe I make it 800. Maybe it's too far, so maybe I make it 0.5 or something. I keep rest the same because these are all temperature dependent, which I don't want to change. All right, so now I have changed the parameters. I go back to my job and I submit again. All right. So it's still running. Let's finish. So I go to results now and I can see everything is working fine. My XY data plots are already there. So since you see you have to do a lot of runs sometimes to identify the parameters, so it might be better to automate at least the post-processing step, right? If you don't know the Python scripting or something like this. So what you can do for post-processing, you can record a macro. So if I go here and I say macro manager, and I can create a macro. So I call it for, let's say, Johnson & Cook, so JC model, right? Something like this. And you can save it in home directory or work directory, again, whatever preference you need. So now it's started recording. So whatever you do here, it will be recording. So first thing you can do is you want to also keep the previous one, because the previous one might be useful for you to see if it's getting better or worse based on the previous results. So let's call this one. So let me first rename this one as previous. So it will record everything now. So this goes to previous. This is first step it will do when you come back again later on. So now it's previous. The second thing you have to do is you have to remove this previous data here from here, because now you need to get the new one. So you have removed that. Now you go and you say ODB as we did before. You have already selected these parameters, LE33 and S33, and you can say element label 1. So everything is now being recorded in this macro. Okay, and done. So once this thing is done now, and now we need to combine it. So again, create, operate on XY data, and then you say combine LE33 and then absolute comma and then absolute value of S33, save, and again keep it default so that it will always, so XY data 1 will always be the new results when you plot them. Then you can just plot these three curves and then you say stop recording. Okay, so now this macro has been recorded. So now this process which we did just now for post processing is just one click away, and I will prove to you I'm correct in that sense. All right, so I have plotted those after changing the parameters, and you can see I'm very close to the experimental curve now by changing the set of parameters. So you see, by changing material parameters, you can also fit the model. And now once you are happy with the fitting, you can say that these are my final set of parameters. So I can go and see, in this case, the parameters which we have identified are the last set of parameters which we used here. All right, okay, so these are the elastic part and these are the plastic parameters. You can say that, okay, the hardening might not be really good or something, so let's change it to something. So let's change it to 0.55. So I'm just changing this value now, and this will also demonstrate that my automation works or not for the case of, but if I use a macro which I just developed. So now I go to the job and then I submit. So it's running. And then it's finished. So I go to the results and XY data manager. Only thing you have to do in this case is, you remember, if you rename this thing to this in that macro, so that's recorded. But since there was no previous data before, so I didn't delete that, so it's not in the macro. So if you run this macro, it will give you an error that there is already data which is with the name previous available. So maybe the only thing you have to do is just delete this previous for the case. But again, if I had this data before, I can have it in my macro, and then I don't need to do it. And now I press run. And so you see, it was just a click of a button, and now my data is updated, everything is new, and this is the plot, which how it looks like. So this was my previous one, if you remember, and when I change my n, now it become this thing. So again, this is too small. If it's too small, you can go and change the font here. and also yep, so this will give you an idea that okay, my XY data is a new one, which is much better than the one, but it's not really good in this area. So if your deformation is mainly in this area, then the previous curve was better. If your deformation is around this area, then maybe this curve might be better. Again, as an analyst, you decide what's better, what is not. So I hope this makes sense. You need to do a lot of runs, and based on that you can identify the parameters, and then once you have identified the parameters from a representative uniaxial test as discussed today, then you can use it for any other real case which you have. Again, imagine if you have strain rate dependency, so you have test data from different strain rates, you can have data for different temperatures, you can have material model which can have more complicated behavior which require a huge number of parameters rather than only 3 in this case, then it's a very tedious job to do it manually, as I showed you before today. So in those cases it might be a good idea to use some kind of automatic identification procedure. So from that perspective, if you look at this, so this is one of the examples from one of our work in my research group some long time ago, but still we are using it. So in this case we use a crystal plasticity model, and again you can see we had a huge number of parameters there. So we need to simulate the stress strain curve. So what we did, we had an experimental data, we simulate by changing these parameters, and you keep on changing it unless we get a good fit. So in this case what we did, we interface this ABAQUS with UMAT and everything with an optimization tool. In this case we use a code which was a open source code at that time, Minuit, and we basically identified the parameters automatically. As you see, it gives a very good fit and a final set of parameters. If this is not available now, you can use MATLAB toolboxes. We have already tried those as well. So you can call ABAQUS from MATLAB. This was Fortran based, so we can call ABAQUS from Fortran as well. We have used C++ based codes like genetic algorithms before. So there are again many different codes available from different national labs from US. So you can use those and interface it as we have done it here. So it's just like a wrapper you have to write, and whatever I did before manually, you try to make it automatic. Recently ABAQUS people also talk about eyesight. Again, I'm not familiar with that, but philosophy is very much the same, so you can try that. And then there is a whole bunch of different types of tools which you can interface and identify the parameters. So I hope this makes sense, and this gives you an idea about different ways of defining material behavior in ABAQUS itself and also in ABAQUS CAE environment directly. If you have any questions, again, it was a quick video. I had to rush in many cases. So if it was the case, then please feel free to ask any questions by commenting below, and please share it to someone who will find it useful. So I will see you in the next video next time. By then, take care. By then, bye bye.